Welcome to MathGPT. Today, we're going to explore blackbody radiation and Wien's law, fundamental concepts in physics that help us understand how objects emit electromagnetic radiation at different temperatures. Let's start by understanding how we visualize the emission of radiation. We'll create a graph where the x-axis represents wavelength in nanometers and the y-axis represents intensity, or how much energy is emitted at each wavelength. Now, let's see how objects at different temperatures emit radiation. I'll plot four curves representing objects at 3000 Kelvin, for 1000 Kelvin, 5000 Kelvin, and 6000 Kelvin. Each curve shows the intensity of radiation emitted at different wavelengths. Let's add the electromagnetic spectrum bands to our graph. On the left side, we have ultraviolet light with wavelengths less than 400 nanometers. In the middle, from about 400 to 700 nanometers, we have visible light, which I'll highlight with a rainbow-colored band. And on the right side, beyond 700 nanometers, we have infrared radiation. Now, let's analyze these blackbody radiation curves. First, notice that hotter objects emit more energy at all wavelengths. The 6000 Kelvin curve is higher than the 5000 Kelvin curve, which is higher than the 4000 Kelvin curve, and so on. Second, observe that as temperature increases, the peak of the curve shifts to shorter wavelengths. The peak for 3000 Kelvin is in the infrared region, while the peak for 6000 Kelvin is much closer to the visible region. This shift of the peak wavelength with temperature is described by Wien's law, which states that the wavelength at which an object emits the most radiation is inversely proportional to its temperature. Mathematically, Wien's law is expressed as lambda maximum equals b divided by t, where lambda maximum is the peak wavelength, T is the temperature in Kelvin, and B is Wien's displacement constant, approximately 2,898 micrometers Kelvin. Let's apply Wien's law to an example. The Sun has a surface temperature of about 5,800 Kelvin. Using Wien's law, we can calculate the wavelength at which the Sun emits the most radiation. Lambda maximum equals 2,898 divided by 5,800, which gives us approximately 0.5 micrometers or 500 nanometers. This wavelength corresponds to green light in the visible spectrum, which is why the sun appears yellow-white to our eyes. Understanding blackbody radiation and Wien's law has many applications. In astronomy, scientists use these principles to determine the temperature of stars. By analyzing the spectrum of light from a star, they can identify the peak wavelength and calculate the star's surface temperature. In engineering, these concepts are used to design and optimize devices like infrared heaters, thermal imaging cameras, and incandescent light bulbs. In everyday life, we observe these effects when objects heat up. As something gets hotter, it first glows red, then orange, then yellow, and potentially white-hot, demonstrating the shift of the peak wavelength toward the blue end of the spectrum. To summarize what we've learned, first, all objects emit electromagnetic radiation across all wavelengths, with the distribution following the blackbody radiation curve. Second, hotter objects emit more radiation at all wavelengths than cooler objects. Third, as an object's temperature increases, the peak wavelength of its emission shifts toward shorter wavelengths, as described by Wien's law. And finally, these principles help us understand phenomena ranging from the color of stars to the design of heating elements and light sources. Thank you for watching this exploration of blackbody radiation and Wien's law.